Hello there. Today we have this wild hyperbolic integral on the channel, and it's the integral from 0 to infinity of x squared divided by the square of the hyperbolic cosine of x squared. So yeah, that's a pretty fascinating structure, and a substitution comes to mind immediately. So let's call the integral I for reference purposes, and the substitution that comes to mind is letting x squared equal to u, which implies that x equals the square root of u, which further implies that dx equals 1 by 2 times square root u du. So our integral I can be written in the u world as the integral from where to where exactly? Well, as x approaches 0, u will also approach 0, and as x approaches positive infinity, u will also approach positive infinity, right? So we have the integral from 0 to infinity of this term, which is now u, and the differential element is 1/2 times u to the negative 1/2 du divided by the square of the cosh of u. And we can write out the numerator as u to the 1/2, of course. And next up, we can expand using the definition of the hyperbolic cosine. So cosh z equals e to the z plus e to the negative z divided by 2, right? So this implies that we can write I as 1/2 of the integral from 0 to infinity of u to the 1/2 du divided by e to the u plus e to the negative u squared. And all of this is divided by 4, so we can just multiply out the whole thing by 4, correct? And we have some nice cancellation taking place. And so this is the structure of our integral I in the u world now. Now, regular viewers of the channel know that I love employing the geometric series expansion. So what I'm going to do next is I'm going to take the denominator and factor out an e to the u term. So I have the integral from 0 to infinity of u to the 1/2 du divided by factoring out an e to the u term, and because of the square I have e to the 2u times 1 plus e to the negative 2u all squared. And of course, we can expand using e to the negative 2u as well. So this cancels out the term in the denominator. And we now have this pretty fascinating structure. Now, how exactly am I about to invoke the geometric series expansion? Well, write this as twice the integral from 0 to infinity of u to the 1/2 times e to the negative 2u divided by 1 plus e to the negative 2u squared. And this is the term which I want to express as an infinite series. And how exactly am I going to do that? Well, the reciprocal of 1 plus x when the absolute value of x is less than 1 can be written as the sum over the non-negative integers k of negative 1 to the k times x to the k. So if I replace x by e to the negative 2 times u, and let me just zoom back in to get a better field of writing. So we have 1 plus, the reciprocal of 1 plus e to the negative 2u being equal to the sum over k of negative 1 to the k times e to the negative 2ku. And differentiating both sides with respect to u gives me the exact structure I have in the integrand. We get e to the negative 2u times 2, and a negative sign over here as well because of the power rule, and we're dividing by 1 plus e to the negative 2u now squared. And on the right hand side we have the sum over k of negative 1 to the k times e to the negative 2ku times negative 2. And the negative 2's cancel out quite nicely. And finally, we have e to the negative 2u divided by 1 plus e to the negative 2u squared being equal to the sum over k of negative 1 to the k times e to the negative 2ku. So this is our target integral written out, and we know what this term here evaluates to in terms of an infinite series expansion. So this implies that we can write I as twice the integral from 0 to infinity of u to the 1/2 times the sum over the non-negative integers k of negative 1 to the k times e to the negative 2ku du. And because this u term outside is independent of the index variable k, we can just slip it inside the integration operator. And we can write this, oh, sorry about that, terribly sorry. we can write this as the integral from 0 to infinity of the sum over k of u to the 1/2 times all of the other stuff. And the golden question here is whether we can switch up the order of the integration and the summation operators. Well, if you look at the argument here, there are no problems regarding boundedness and convergence, especially thanks to this damped exponential factor. So yes, we can perform the switch up, and we can write this as twice the sum over k of the integral from 0 to infinity of u to the 1/2 times e to the negative 2ku. And what about this term here, negative 1 to the k times k? Well, they're independent of the u variable with respect to which we're integrating, so we can write them outside the integration operator as constant multiples in the integration world, in the u world, that is. So we have negative 1 to the k times k being multiplied by this integral. And one thing to notice here, that if we take the value of k equal to 0, then we have 0 times the integral. So yeah, that amounts to a big fat 0, and we can just ignore that term and start our sum at k being equal to 1. And now for another substitution that, again, regular viewers of the channel probably saw coming. I'm going to take the argument of the exponential function here, that's this 2ku term, and I'm going to let it equal to another variable t, which implies that u equals 1/2 times k times dt, right? Du, that is in the I'm talking about the differential element. So this implies that I equals twice the sum over the positive integers k of negative 1 to the k times, again, the limits of integration are not bothered by our transformation. And we have u to the 1/2, and u becomes t divided by 2k. So all of that in square roots now. And we have e to the negative t. And what about the differential element? Well, the differential element is dt divided by 2 times k. Okay, cool. And again, the k terms, the terms involving purely k, are independent of the t variable, so we can just take them outside the integration operator, blah, blah, blah. We have some nice cancellation. 2 times the sum over the positive integers k of negative 1 to the k. Oh, terribly sorry. Negative 1 to the k. And 1 by the square root of 2 times 2. So again, you have some cancellation here as well. So 1 by the square root of 2 times k times the integral from 0 to infinity of t to the 1/2 times e to the negative t dt. So we have a familiar favorite, the gamma function, and this is the gamma function with the argument equal to 3 by 2. So this implies that I equals, wait a second, I had gotten rid of this 2, right? So yeah, there you go, we're rid of this 2. So I equals the sum over k of negative 1 to the k divided by k to the 1/2, and we're going to write this reciprocal of square root of 2 outside because it's just a constant multiple. So we have this structure here times gamma 3 by 2. So gamma 3 by 2 just sorts out to be 1/2 of the square root of pi, correct? So finally, we can write I as 1 by 2 times square root 2 times the square root of pi times the sum over the positive integers k of negative 1 to the k divided by k to the 1/2. And it was at this stage of recording that I realized I fucked up big time. And yeah, I'm missing a negative sign. And my mind immediately went back to the differentiation. And yeah, I was correct. That's exactly where I missed the negative sign. So remember me expressing 1 by 1 plus e to the negative 2u as the sum over the non-negative integers k of negative 1 to the k times e to the negative 2ku? And that was cool. But next up, I had to differentiate with respect to u, right? So because of the power rule, I have this negative 1 term in the numerator. And downstairs, I have 1 plus e to the negative 2u squared. And now because of the chain rule, I have this negative 2 times e to the negative 2u. So you see how nicely these negative signs cancel out, right? So yeah, I wish I could appreciate this nice cancellation earlier. So yeah, my bad. Anyway, on the right, you have the sum over k of negative 1 to the k times e to the negative 2ku times negative 2k. So you still have this nice cancellation of the 2's, but you still have this negative 1 now attached with the k. And negative 1 times negative 1 to the k means that you have negative 1 to the k plus 1. So that's pretty much it. That's the only mistake in the video, and that's been corrected pretty easily. So all I have to do is replace this k with a k plus 1, and now I have to give myself some writing space, and I have this really nice result that I can express in terms of the Dirichlet eta function. So we can write I as the square root of pi divided by 2 times the square root of 2 times the Dirichlet eta function evaluated at 1/2, which itself is a very beautiful result. I mean, I like this. I really do like this. It's a really wonderful sight to look at, but perhaps you can improve on it by using the Riemann zeta function, as there is this beautiful relationship between the Dirichlet eta function and the Riemann zeta function by eta of s being equal to 1 minus 2 to the 1 minus s times the Riemann zeta function at s. So using s being equal to 1/2, we have 1 minus the square root of 2 times the Riemann zeta function evaluated at 1/2, which of course is defined because of the analytic continuity of the zeta function. So finally, we can write our integral I as the square root of pi divided by 2 times the square root of 2 times 1 minus the square root of 2 times the zeta function evaluated at 1/2, which is quite a nice result indeed. So let me know in the comments which result you liked better. Was it the one in yellow with the Dirichlet eta function or the zeta function? And I hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.